All right, so we're here to talk about Polya counting, and in particular, the Polya enumeration theorem, which is going to let us answer, again, questions of this form for just about any structure that you could describe as having nodes and symmetries. But we're going to need some terminology first. So before we can state the Polya enumeration theorem, I want to go ahead and describe sort of our basic setup here. So our basic setup here is going to be that we're going to have some structure. It's going to have some big N. This is going to be our set of nodes. Okay. And as I define these terms, I'm going to go along with our 6-bead necklace and talk about what this is. So in the case of our 6-bead necklace, the 6 nodes are the 6 places I'm going to put beads. 1, 2, 3, 4, 5, and 6. Okay, and so I'm going to label these 1, 2, 3, 4, 5, and 6. So that means in this example, our set N is the set 1, 2, 3, 4, 5, and 6. Okay. Additionally, past the set of nodes, we need to have a way of talking about symmetries. Okay, and so the way I'm going to describe the symmetries is as a function from the set of nodes to the set of nodes. So describe each symmetry G as a function f from n to n. Okay. And so what that's going to mean is I'm going to look at these labeled nodes, and I'm going to describe, okay, for each symmetry, where does each of those things go? Okay, and so as an example, back in our case of this 6-beaded necklace, one of our symmetries is just a rotation. So I'm going to call that symmetry R. And if I think of R here as a function from n to n, that means I have to say where does 1, 2, 3, 4, 5, and 6, where do they all go? Okay, and so this 1, it's now going to what was before called 2. The 2 is going to what was before called 3. 4. The 4 is going to 5. The 5 is going to 6. And then the 6 ends up going back here to 1. Okay, and so this is one of the symmetries of our 6-bead necklace. Okay, so that's our first character in the cast that's going to appear in our first 2 characters that are going to appear in our cast in our Polya enumeration theorem. We have a set of nodes, and then we have some symmetries, which are all defined explicitly as functions from the nodes to themselves. Okay. We're going to go ahead and give a name to the set of all the symmetries. Okay, and the reason I'm calling this big G is because this set forms a group, although we don't need to know anything about groups to explain and understand what the theorem says, but that's just what I'm going to call it. Okay, and so in our example, if we write down the symmetries, back of our, again, the symmetries of our 6-beaded necklace here, we know, I think, that there are 6 symmetries that correspond to the rotations. So I'm going to give them all names. Okay, so there's the symmetry, and there's always going to be the symmetry where we don't do anything. So I'm going to call that id. Okay. And then there's the symmetry we already named R. Okay. And then there's rotate, but instead of rotating one notch, rotate two notches. And so I'm going to call that r squared, because that's going to be rotate and then rotate. And likewise, there is rotate 3 times, which I'm going to call r cubed, and then 4 times, which is going to be r to the 4th. And then finally, there's rotate 5 times. And probably if you were to actually look at the rotation 5 times, you might be more inclined to describe that as a counterclockwise rotation by 1, but we'll go ahead and write it this way anyway. And so whenever we've talked before about symmetries of some sort of circular arrangement like this, we've always really been talking about sort of do a rotation once or twice or 3 times or whatever. Or really, if you want this id here, that's just r to the 0th. That's saying you don't rotate any times. Okay, so that's sort of the way we're going to encode this description of what we mean when we're talking about symmetry. And that's really going to be important to describing how this is going to work in general. Okay. And the next thing we're going to need to talk about is we're going to need to talk about orbits. And so this notation I'm going to use here, I'm going to talk about this. This is the orbit of the node n under the symmetry G. Okay. And so what is this? If I think about a specific case, so let's think about a specific case here. So I'm going to do O r squared of 1 back in our 6-bead necklace here. The orbit is going to be the places you can get by using that symmetry from that node. So if I'm looking at the symmetry r squared here, again on our 6-bead necklace, there's 1, 2, 3, 4, 5, 6. If I start here at node 1, and then I apply this r squared symmetry, where do I end up? Well, I end up down here at 3. And then if I apply the r squared symmetry again, then I end up here at 5. And then I end up back to 1, and back to 3, and back to 5. And so what we're really observing here is that under this symmetry r squared, these 3 points are tethered together. Okay. And likewise, under the same symmetry, if I instead started at 2 and then applied r squared, I'd end up at 4. And then I'd end up at 6, and then I'd end up back at 2. And so again, under this r squared symmetry, these 3 points are also tethered together. Okay. And so the way we're going to write that is to say, okay, the points that are tethered together with 1, well, 1, but then 1 also gets connected to 3 and 5. And likewise, if I were to take O of r squared 2, that would end up being 2, 4, 6. Okay. Now note if I took OR squared of any of these, so if I took OR squared of 3, I'm going to end up back in the same collection of points. And if I took OR squared of 4, I would end up in this collection of points. So really, there's only 2 orbits of r squared. There's this orbit, and there's this orbit. Okay. Let's do another example. Let's see what happens if I instead look at the orbits of just r. So start here at 1, And look at our necklace again. And there for this one, if I start at 1, and then I apply the rotation, then I end up at 2, and then I end up at 3, and then 4, and then 5, and then 6, and then finally back at 1. And so what that's saying is under this symmetry, actually, all of these things end up in the same orbit. So here there's one orbit. All of these points get sort of mixed up together by this symmetry. Whereas back in this previous instance, only these 3 points got mixed up together, and only those 3 points got mixed up together. Okay, so there are 2 more examples I'd like to do, just to make sure we're super on the same page. Okay, so I want to look at O, the identity. And so this is the symmetry, remember, that doesn't do anything. So if I look at where 1 goes under this symmetry, 1 doesn't go anywhere. So the orbit of 1 is 1. If I look at 2, it doesn't go anywhere, so the orbit of 2 is 2, and so on. So here the orbits end up being that, 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 and that. Okay, whereas here I only had 1 orbit, which consisted of all of my nodes. Okay. Last up, and you probably want to pause and make sure you're happy with what's going on before I spoil this one for you. But look at what O of R cubed is. And look at what the orbits of these are for 1 and 2 and so on and so forth. Okay. Assuming you've done that now, so I will ruin the surprise for you. And so let's look at our things. 3, 4, 5, 6. There's our necklace. And so under R cubed, where does 1 go? Well, 1 goes to 4, and then 4 goes back to 1. So these are linked. Okay. Likewise, if I start with 2, where does 2 go? 2 goes to 5, and 5 goes back to 2. So those are linked. And then 3 goes to 6, and 6 goes back to 3. So those are linked. So what that says is there are here 3 orbits under this symmetry. Namely, there is 1 and 4, and there are 2 and 5, and 3 and 6. Okay. I'll leave to you to do for me the 2 we haven't done. So what are OR to the 4th? What are the orbits of this? And OR to the 5th? What are the orbits of this? Okay, so I will leave these for you to go ahead and do. All right. So we have one more thing we need to define. And so that thing that we need to define is we need to define what we're going to call the cycle number. And so the cycle number of a symmetry little g. Okay, and again, I'm just calling the symmetry little g because it's an element of big G. The cycle number of the symmetry is just the number of orbits. It's the number of orbits of little g. Okay. And so going back to our examples, here there are 3 orbits. So what that's saying is that c of r cubed is 3. Here there was 1 orbit, so c of r is 1. Here there are 6 orbits, so c of id is 6. And here there were 2 orbits, so c of r squared is 2. Okay, so again, before we get to the next video, make sure you can tell me what c of r to the 4th is and what c of r to the 5th is in our particular example. And when we come back, we'll be able to state, now that we have all of these characters, the full Polya enumeration theorem.